Hello friends, in the last class we were discussing about the mix design concepts of reclaimed asphalt pavement materials, and we discussed about the use of blending chart, and we completed our discussion on the use of viscosity blending chart in case we are looking at the viscosity grading system. So, viscosity blending chart can be used, and then we looked at two cases. One was to determine the grade of the virgin binder to be used when the wrap percentage is fixed, and we also know the grade of the target binder. And the second case was that we are trying to find that what will be the maximum percentage of wrap to be used when the grade of the virgin binder is fixed and also the target grade of the final mixture is also fixed. So, today we will look at the PG grading system, taking similar examples of these cases, and then we will try to see that what are the steps when we talk about the PG grading system. So, as I mentioned, in the PG grading system we have three set of tests. We have high temperature PG corresponding to 2.2 kPa, we have intermediate temperature PG corresponding to the value of G star dot sine delta of 5000 kPa, and then we have low temperature PG criterias based on the value of creep stiffness and the value of M or the creep slope. So, we will try to look at the use of this blending chart in case of PG grading system again with examples. So, let us say that 30% wrap has to be used in order to produce a blended binder of grade PG 64-22. So, this is the target grade we are looking at, and 30% wrap we are utilizing, which means I am trying to find out what should be the appropriate grade of the virgin binder for considering all these three criterias. Recovered wrap binder properties are shown in this particular table. So, we have taken the recovered binder, we have subjected it to testing, and we know we have discussed how to do the testing, and this is what we have got. So, this is the critical temperature which means the true fail temperature corresponding to 2.2 kPa, it is 86 degrees Celsius, 31 G star dot sine delta, value of S minus 14 and value of M minus 11. So, the true grade becomes 86 minus 11, whereas the actual grade becomes as per M320 it becomes 82 minus 10. Okay. But as I mentioned, we will use this particular temperatures to do our calculations. All right. So, before I show you the calculation, let us try to understand the linear blending process here without using any charts, just by hand calculation. So, critical temperature of virgin grade, because this is what we are trying to determine, will be evaluated using linear blending. So, what do you mean by linear blending? So, say that y percent of wrap binder, when I say wrap binder or wrap, I am just indicating the same thing here. So, a wrap binder has to be used. Okay. So, when it is y percent wrap, which means 1 minus y is the virgin binder in the total mix, is not it. So, y 1 minus y is the virgin binder. Let us say linear blending says that y into the critical temperature of wrap plus 1 minus y into the critical temperature of the virgin binder will give you finally 100 into the critical temperature of the blend. Okay. So, this is the basic formula for blending. So, in this particular case we are trying to determine Tc for virgin binder. So, Tc for virgin binder is basically equal to Tc of blend. If I am considering this in fraction, so this cannot be 100, this will be equal to 1. So, Tc of blend minus y times Tc of wrap divided by 1 minus y. So, this will be the formula which we will be using in this particular case where we are trying to determine the appropriate virgin binder grade. All right. So, for all the three cases of critical temperatures. Now, here again we will do some rounding off once we determine the value. We will discuss why the rounding off is done, but you have to remember that we have to round up when we talk about high PG, alright, and we have to round down for intermediate and low temperature values. Why? Because this will give us a more conservative approach. We will discuss why I am saying that the approach will be conservative. Let us look at the example. These formulas which we have discussed, first we have calculated what will be the critical temperature for high PG. This table shows us the value which we have obtained using the linear blending which we have just discussed. So, this is for high PG. So, how they arrived at this 55? We use the similar formula which I just wrote before some time, that for Tc high of the virgin binder grade will be equal to how much? It will be equal to 64. This is the target grade minus 30% wrap to be used, 0.3 into the Tc of wrap is equal to 86, which is given, divided by 1 minus 0.3. If you do this calculation, you get the value as 54.6, alright, and as I said, we have rounded up, which means 55. Why they have taken 55 here? Because if we assure that the virgin binder grade which we are going to use satisfies the criteria of G star dot by sin delta at 55, it will definitely satisfy at 54.6 degrees, okay, if it satisfies at 55 degree, okay, and that is why a rounding up is done. Similarly, you can calculate for G star dot sin delta using the same formula. If you calculate, you get as I am just showing you the example for intermediate, it is 25. Why it is 25? Because it is 64 minus 22. So, this is how much? 42. So, 42 divided by 2 plus 4. This is our calculation which we have seen previously while discussing about PG grading system. So, 21 plus 4, 25. So, the target grade is 25. So, 25 minus 0.3 into 31 which is given, divided by 1 minus 0.3. So, this gives us as 22.4, but they have taken as 22. Why they have taken as 22? Because if the value of G star dot sin delta is less than 5000 kpi at 22, it will definitely be lower at a higher temperature of 22.4. So, the criteria gets satisfied, and similar discussion will go for the low temperature values. Okay. So, this is what they have obtained, which means that the binder grade which we are targeting, the critical grade should be PG 55 minus 27, and the actual grade as per M320 should be ASTO M320 should be PG 58 minus 28. So, this process tells us how to select the appropriate PG grade, considering that the percentage of wrap binder is fixed and the target grade is fixed. Okay. So, this is the first example. Before we discuss about the second case, there is a note here that to meet the intermediate temperature criteria, the critical temperature should not be higher than 22 degrees Celsius. Alright. So, this tells us that though you have got the final grade, that is PG 58 minus 28, but this shows only the high temperature and low temperature. It does not tell us about the intermediate temperature. But you see, if you do the calculation, which is 58 minus 28, so this is 30 divided by 2 plus 4, so this is 19 degrees Celsius. So, as per the calculation, it tells that the critical temperature should not be higher than 22 degrees Celsius, and if you take PG 58 minus 28, it is 19 degrees Celsius. So, this satisfies the criteria and we do not have to worry about the intermediate temperature here. Okay. So, now let us move forward with the second case, that I want to determine appropriate wrap percentage. Again with the example, let us say that we have a virgin binder grade PG 58 minus 22 to be used with a given wrap source in order to produce a blended binder of PG 64 minus 22. So, the target binder is fixed, the virgin binder to be used is fixed, and we have to determine what is the maximum percentage of wrap which I can use, or what is the range of wrap percentage I can use considering all the three criterias. The recovered wrap binder properties and the critical temperature of virgin binder, which means PG 58 minus 22, are shown in the table. So, this is the table and you see that we have the virgin binder which has a high PG of 61. For wrap binder we do not determine the original binder grade, so not required. RTFO 61, wrap binder is 86. Intermediate G star dot sin delta less than 5000 kPa, 15 degrees Celsius in the virgin grade, 31 degrees for a wrap binder. The value of S corresponding to the BBR test is minus 32 for virgin binder, minus 14 for wrap binder and this is minus 29 and minus 11. So, this is what is there, what is given. The actual binder grade and M320 is indicated here. Okay. So, this is what is given to us. Now, let us talk about the steps. Again we will use the linear blending formula to determine the proportion of wrap binder to be used for producing Pg 64 minus 22. Talking about the same formula which I just wrote in the previous slide, we wrote that Y into T of wrap plus 1 minus Y into T of virgin binder is equal to T of blend, is not it. So, in this particular case we are trying to determine the value of Y. So, Y becomes equal to T of blend minus T of virgin binder divided by T of wrap minus T of virgin binder, alright. I think this is right, yes this is right, okay, virgin binder. So, this formula we will use to calculate the value of Y for all the different cases. So, let us look at the calculation for each cases. Okay. Let us say that first we are looking at the value of Pg high. So, when you do the calculation for Pg high, Y becomes equal to how much? 64 is the target value minus 61 is virgin binder divided by wrap which is 86 minus virgin binder 61. This gives us 0.12, which means that at least 12% of wrap will be required such that the value of G star by sin delta of the final blend is more than 2.2 kPa. Because you see the value of G star dot sin delta will be higher only when the stiffness is higher. So, this is the minimum value which is desirable, which means that can we go up to 20%, can we go up to 30%. So, in order to ensure that the selected wrap percentage does not give us a PG grade to the next PG grade, which means we are not landing at PG 70, we have to also find out the maximum value here. So, this is the minimum value. So, that is why it says calculation gives minimum for PG high. Okay. So, we have to find out the maximum value also. So, in order to find out the maximum value, what we have to do for finding out the maximum value, take 1 degree lower than the next higher grade. So, next higher grade is PG 70. So, I will ensure that it is not beyond 69. So, how do I do the calculation here? 69 minus 61 divided by 86 minus 61. So, if you do this calculation, you will get the value as 0.32, alright. You will get the value as 0.32, which means that the wrap binder should not be more than 32%, so that it goes to PG 70, alright. So, as per the high temperature PG, the range is 12 to 32%. Talking about the intermediate temperature now, what we have to do, we will use the same formula, Y is equal to 25 is the target minus 15 divided by 31 minus 15. If you do the calculation, this is 0.62. This value is the maximum, which means in order to satisfy the criteria of G star dot sin delta less than 3000 kPa, the percentage of wrap should not be more than 62%. Because if you go more than 62%, you will have a stiffer binder and which will not be sufficient to satisfy the criteria of our target grade, alright. So, this is the maximum, and that is why it is written that calculation gives minimum for PG high and maximum for other temperatures. So, this is 0.62. If the designer is interested to find out the minimum value corresponding to intermediate temperature also, then similar to PG high, what we will do? We will take 1 degree higher than the next lower grade. Okay? For intermediate temperature, the grade changes by 3 degrees Celsius. So, when it is 25 now, it should be how much? 23 degrees Celsius. Next lower grade is what? Minus 3. So, it is 22, 1 degree higher than the next lower grade. So, 23. So, we will do the calculation as 23 minus 15 divided by 31 minus 15, and if you do this calculation, you will get the percentage of the minimum percentage corresponding to intermediate grade. But it is not very important for us to determine the minimum percentage corresponding to the intermediate grade here. Alright. Now coming to the last aspect that we also have to find corresponding to the low temperature. So again, Y corresponding to the value of creep stiffness is what? Minus 22 is the target, minus of minus 32 divided by minus 14 minus 32. Okay. So, this gives us a value of 0.55. So, similar to intermediate temperature, this is also the maximum value. So, this is the maximum value corresponding to the stiffness value, the value of S. Alright. Now, corresponding to M value, it will be how much? This is corresponding to S, corresponding to M, it will be minus 22 minus 29 divided by minus 11 minus 29. So, this is equal to 0.38. So, 38% maximum corresponding to M. Here the designer might be interested also to find out the minimum value, just to ensure that he is not using excessively soft binder, okay, corresponding to low temperature. So, what he has to do, again follow the same thing, take 1 degree higher than the next lower grade. So, the present grade is minus 22. So, the next grade is minus 28. So, I will take minus 27 degrees Celsius for calculation. So, corresponding to S value, it will be minus 27 minus of minus 32 divided by minus 14 minus 32. So, the minimum value corresponding to S is 0.28, and minimum value corresponding to M is minus 27 minus 29, alright, divided by minus 11 minus 29. So, this is equal to 0.11, 11%. Okay. So, which means that for lower temperature, a range between how much? 11% to 38% should be chosen. So, just a recap, high temperature was 12% to 32%, intermediate was it should be less than 62% or 0.62 I am saying. In order to satisfy the low temperature grade, it should be between 0.11 to 0.38. Okay. So, looking at all these three values, what we can finally conclude, that we can take the final wrap between 12 to 32. So, if we take 12 to 32, it will satisfy all the criterias, okay, and which means up to maximum 32% is permissible in this particular example. So, if we take the wrap binder between 12 to 32%, it satisfies all the desired criteria, alright. So, I hope that this is again clear to you that how we do the calculation in case of PG grading system, a little more cumbersome than the viscosity grading system, but very easy to understand. Alright, now the final steps of mix design, that we have to determine the combined aggregate gradation. This is very simple. We have to remember that the wrap stockpile is not equal to the total wrap which is chosen, because in the wrap aggregate we have the binder coated with it. So, we have to remove the binder in order to know the quantity in the stockpile. So, the wrap stockpile is equal to wrap chosen minus the amount of binder in the wrap. Okay. So, this is very simple to understand, and once we have the wrap stockpile, then we have to adjust the other virgin aggregate stockpile which have been determined corresponding to the chosen wrap value. Now, this can be understood with an example. Let us say that the chosen wrap is 20% and the other stockpiles are taken as 30%, 30% and 20%. So, the summation is 100%. But this cannot be the exact stockpile, because wrap chosen is not wrap stockpile. So, we will determine first that what is the wrap stockpile here. So, wrap stockpile is wrap chosen minus percentage of bitumen in wrap divided by 100 into wrap chosen, which is 20%. Okay. So, and we will adjust the other stockpile. So, how we adjust the other stockpile? By proportioning. So, this is the difference we are obtaining, is not it? Wrap chosen minus wrap stockpile. This amount we have to adjust in other stockpile. So, what we are doing? We are increasing the other stockpile by corresponding to the proportion of the remaining stockpiles. So, just to avoid confusion, you look at these three values A1, A2 and A3. Okay. So, what is the proportion of A1 corresponding to A1, A2 and A3? It is 30 divided by 30 plus 30 plus 20, okay, which is 30 divided by 80. So, this is the proportion of A1 corresponding to the virgin stockpile. So, similarly the proportion of A2 is 30 divided by 80 and the proportion of A3 is 20 divided by 80. So, we will adjust this particular value in the other stockpile corresponding to their individual proportions. So, that is why A1 we will increase by A1 of A1 chosen plus this particular value. Similarly, A2 will be A2 plus 30 by 80, same thing, wrap chosen minus wrap stockpile, and A3 will be A3 plus 20 by 80 into wrap chosen minus wrap stockpile. Okay. Alternatively, what we can do the straightforward calculation, then that when we are doing the gradation, we can at the initial stage use the stockpile value and then determine the value of A1, A2 and A3 instead of back calculating and adjusting the gradation. Okay. Then during the laboratory mix design, we have to ensure that we are not heating the wrap beyond 110 degrees Celsius for more than 2 hours. Because this can cause generation of flames and excessive aging of the wrap binder, alright. And then total virgin binder to be added is equal to the difference in weight of the binder to be added in the new mix and weight of the binder present in wrap. Well, this is very straightforward, we already know. For example, if the wrap binder is 2% is available and the optimum binder content is 5%, then we only have to add 3% virgin bitumen to make the mix, which is of course very straightforward. Well, the other mix design principles remains the same that we have discussed for hot mix asphalt, that is preparation of mix, analyzing the volumetrics, doing the performance testing and so on. Alright. So, with this we complete the mix design concepts related to wrap, and some of the ending notes are some of the pictures which I will show from a few site visits carried out in India. Now, you have to remember that though we are discussing about increasing the quantity of wrap, but there are challenges especially related to the plant operation, because wrap you cannot heat directly to elevated temperature. So, for example, in a batch mix plant we have heating drums where aggregates are exposed directly to the flames at very elevated temperatures, and this is not permissible for wrap. So, there are adjustments which are done sometimes in the plant, or if these adjustments cannot be done, then we have to restrict the percentage of wrap to be used in the mix design. So, some cautions have to be exercised before we can successfully implement higher dosage of wrap in the construction of bituminous mixes. So, this is one example where you see what they have done. They have made an arrangement in the drum where the wrap comes somewhere in the middle portion of the drum and it is not directly exposed to the flames, rather it moves only at the periphery of the drum. So, it is not direct exposure, alright. And this system is applicable, they have made this system for only coarse wrap, the reason being the coarse wrap has lower binder content. If they would have inserted even fine wrap here, this could lead to choking of the drum, which is not desirable, and therefore, only the coarse wrap is heated in this form. The fine wrap is basically taken in this conveyor belt and it is taken through the hot elevators and it is directly sent to the pug mill for mixing with the other materials. So, here you can see this is the cold wrap fine, and this finally goes into the pug mill for mixing. This is an example of one typical plant. This is an example of another typical plant. Here basically they had only one conveyor belt for coarse as well as fine wrap, and they were not subjected to any heating mechanism. So, this drum is used only by the virgin aggregates, and this particular conveyor belt is used to transfer the coarse and the fine wrap mixed together, which meets the other aggregates at the end of the heating drum. Alright. So, it was found that once this heated aggregates meets this cold wrap aggregates at the end of the heating drum, the temperature of the mix reduces by around 20 degrees Celsius, considering that the wrap used was 25%. So, the question is what to do here. Then we have to think of other mechanisms, maybe using rejuvenators, maybe heating the aggregate, superheating the virgin aggregates, using additives such as warm mix additives to prepare a proper mix having similar workability and so on. So, there are other aspects which need to be looked at in the mixing plant before exercising the use of a higher dosage of wrap. Another problem is stockpiling of wrap. Unlike aggregates, we cannot allow the wrap to be exposed to large amount of moisture, because moisture retainment is very huge in case of wrap, and we have to remember that wrap are not typically heated to higher temperature. So, moisture cannot be removed very easily as it can be removed from virgin aggregates, and therefore, wrap stockpile should be done using proper shades, so that wrap is not exposed to large moisture content, otherwise this wrap will become non-usable. Well, these are some pictures taken from one of the section where they constructed a DBM mix, dense bituminous macadam, a binder course used in India with 25% wrap, and this was feeded cold surprisingly, and they used ready set to have a uniform mixture and to have more haulage distance so that the temperature drop could be minimized. And this picture was taken after one monsoon period, and I visited this site and we observed no distresses in the field, and you can see that this is a typical surface, a picture which I took with no surface cracks, and we are waiting like how this particular section will perform in the future when it is further overlaid with a wearing course. Alright, so we end here discussing about the mix design of wrap, and we have covered various aspects related to the mix design, and I hope that this presentation was useful to you. And in the next presentation we will talk about the mix design concepts for cold bituminous mixtures. Thank you.